Hi, my name is Kyle Liu, and this is my presentation about hydrogen production for non-potable water using low-cost nickel electrodes. So, about the fundamentals of water electrolysis, this is known as the process of using electricity to decompose water into hydrogen and oxygen using two electrodes, the cathode and the anode. Cathode being the site of reduction where hydrogen gas is produced, and the anode of where oxidation occurs and where oxygen gas is produced. So why am I going to be using nickel for my electrodes and why does structure matter? Well, nickel has high catalytic activity, it is very earth abundant, and has amazing electrical conductivity, while electrode structure matters because a greater surface area can provide for more available reaction sites, with porous structures improving hydrogen bubble release, which allow for faster reactions, as seen to the image on my right side, where every single possible hair on that electrode could be a possible reactive site in comparison to just a flat nickel strip. So, during the study, my control will be my conventional nickel strip, my experimental will be my low-cost nickel-plated steel wool, and I'll be comparing the effects of electrode architecture on hydrogen production. So, about non-potable water as an alternative feedstock, the system usually requires a continuous supply of purified fresh water, with this leading to a heavy impact on our environment as already only about 3% of Earth's water is considered fresh water. So my challenge is to evaluate electrolysis performance in non-potable water amongst three things: gray water, rainwater, and tap water. Gray water being the byproduct of washing, rainwater being the naturally occurring water that comes out of the atmosphere, and tap water being the recycled water that comes out of hoses and taps. For my purpose, I will be seeing the feasibility of low-cost nickel-based electrodes for hydrogen production using alternative water sources. I'll be comparing hydrogen production between flat nickel strips and nickel-plated porous steel electrodes, and I'll be evaluating the effects of tap water, rainwater, and gray water on electrolysis performance. So for my pathway, I have five steps. First one being electrofabrication, second being water preparation, third being electrolysis testing, fourth being hydrogen collection, and fifth being data analysis. For my methodology of porous electrofabrication, I will be using two things: steel wool from a hardware store as seen to the left side, and to my right will be my nickel anode. This will be the sacrificial one, meaning that it will move its own nickel ions onto the steel wool, plating it. This was a 3-day process, which then resulted in my own nickel-coated porous electrode, around a 23-gram mass increase, an increased active surface area, and a more rigid conductive structure. For my methodology, as seen to the left side, these are all my materials, and to the right of that will be all of my entire setup. So this consisted of a cathode and the anode. Usually these two will be plunged into my feedstock, which is my water plus my sodium bicarbonate electrolyte. These two would then be submerged, with the cathode being surrounded by a container. This container would then be filled to the brim with water in it, with not a single air bubble within it. Using a process called gas displacement, I am then able to calculate the amount of H2 that I have just produced by trial. So, as H2 begins to enter the container, it would then begin to push out water, displacing it as H2 begins to accumulate at the very top. Using the formula found down below, I would then find the total container volume before reaction. I'll then subtract off the milliliters of water left after reaction. Finding this difference, I was then able to find the H2 that I had just collected by trial. So for my feed water properties, pH was nothing very remarkable, but TDS and salinity were. TDS being the amount of dissolved solids and ionic content within each source, being basically the minerals, particles, contaminants basically within it. And for salinity being the amount of dissolved ions within the water, leading to increased conductivity if there's more. So as we can see, rainwater had the lowest amount of dissolved solids and ionic content, which was very interesting. And for salinity, it had also the lowest amount of conductivity. For gray water, it had the highest amount of TDS, meaning that it had the most technically minerals and contaminants within it. And for my salinity, it had the highest, once again, amount of ions within the water, most likely due to the soaps within it. For my results of hydrogen production performance, we see to the far left, this is my tap water, and comparing the two of flat nickel strips and porous nickel electrodes, the porous only had around a 1 milliliter increase, For rainwater in the middle, this was the most amount of hydrogen produced out of the two experiments, with the porous nickel steel wool featuring around a 20 milliliter hydrogen increase. And to the right of that will be my gray water, which showed a moderate amount of H2 produced, with the porous nickel steel wool in this one actually featuring a break in the trend, with it actually slightly suffering in the gray water conditions in comparison to my flat nickel strip by around 15 milliliters of hydrogen. So this is most likely attributed due to the fact that gray water can feature different physical and chemical properties by trial, with water contaminants greatly influencing electrolysis performance, which most likely is the result of my decreased performance within my steel wool. For electrical data, I collected this during the trials with the current and time being used to then find the charge passed. Using the charge passed, I was then able to calculate the theoretical maximum amount of H2 that I could collect if my reactor had ran at 100% efficiency. To the right of that will be my experimental H2, which was the amount that I had actually collected. And to the right of that will be my faradic efficiency, which measures the electrical to hydrogen conversion efficiency. So, as we know, tap water and rainwater produce the most amount of hydrogen, with it being the most improved by. As we can see in the tap water porous nickel trial, there was around a 7% efficiency increase for electrical to hydrogen. And for rainwater porous nickel, the trial, there was around a 5% increase, with the gray water porous nickel featuring around a marginal loss compared to that with its flat counterparts. For the cost efficiency of unit fabrication cost of the porous nickel and flat nickel, the porous nickel costs around 50 cents to 65 cents to make, and the flat nickel costs around $4.25 to purchase. Out of the six, we can see that the tap water flat nickel trial featured the lowest amount of hydrogen yield per dollar, with only around 3.1 milliliters of hydrogen produced per dollar that was spent. Instead, the highest was the rainwater trial with the porous nickel cost with around 114.2 milliliters of hydrogen produced per dollar, showcasing that this trial featured the most amount of return on investment and possibly the most amount of possibility for larger scale production in the future. For my calculation proofs, my limitations of bench skill testing, limited trial conditions, electrodurability, and gray water reliability, specifically when bubbles in chemistry relate to what contaminants are within the water, resulting in variable outcomes depending on situation on a case-by-case basis. My conclusions finding that the porous nickel electrode had actually produced greater hydrogen output while increasing electrical to hydrogen conversion efficiency by 7% in tap water and 5% in rainwater feedstocks. Around a 8.7 times greater hydrogen yield per dollar compared to that with its flat nickel strip counterpart, and H2 was successfully generated from all three water sources, demonstrating the feasibility of freshwater independent electrolysis. For my future directions, I hope for real-world implementation of household and municipal wastewater systems, hydrogen energy applications of gray water storage and conversion, hydrogen fuel cell vehicles and industrial hydrogen production, advanced electrode development in catalysts, coatings, and reduction of costs, and for hydrogen energy to be more widely available and more affordable worldwide. References and acknowledgements. Thank you.